All right, are there any questions? Any questions? So then we'll take off from where we left last time, right? I was on the last page of this COD explain uh, handout or explanatory material. I was on this page, right? And we had gone ahead and derived this analytical expression for the COD in the case where you're doing linear prediction of one random variable using the other one, right? Uh, now I also want to cover a special case, right? If you have two random variables that are jointly Gaussian, right, then special things are going to happen, right? So if we employ only the correlation coefficient rho yx between the two normal random variables x and y, then our understanding concerns the prediction of y from x. So you'll observe one of the random variables, you want to make an estimate of the other one, and you're going to use a linear formula of the form y hat equals a hat x plus b hat, right? So when the two random variables are jointly Gaussian, right, the conditional density function also is Gaussian, right? And in this case, actually the conditional mean, right, uh, is given by a linear expression, right? So if it happens that x and y are jointly Gaussian, then the best predictor is linear, and its error is given by this expression, and the expression for the COD is equal to the square of the correlation coefficient, right? So how do you show that? And again, this is something, I mean, all of you have taken undergrad courses in random processes and probability and so on. This is just an exercise in that. So if you have two random variables x and y that are jointly normal with correlation coefficient rho, then we know that the joint density is going to be given by an expression of this form, right? Rho is the correlation coefficient, mu x is the mean of x, mu y is the mean of y, right? This is the expression, right? Now, in this case, the marginal random variables x and y are also normally distributed, right? Because if you integrate out over y, then you're going to get the marginal density for x. Okay, that is also normally distributed, and they have means mu x and mu y, and variances sigma square x and sigma square y. So the density function for x is given by the following expression, right? Oops. So the density function, if you integrate this out over y, you will get this density function, okay, which is that for a univariate normal, all right? Now, to get the conditional density function, because remember, the best minimum mean square error estimate is the conditional mean, right? So if you have the conditional density, you can calculate the conditional mean from that. So to get the conditional density function, you're going to divide the joint density by the marginal density, right? And you get this expression. Well, this also looks like a normal, looks like the probability density function of a normal random variable, right? Where the mean in this case is basically whatever is sitting here, right? Mu x, whatever, mu y plus rho sigma x over sigma y over sigma x times x minus mu x, right? That is the expression for the conditional mean, right? So the conditional density is a univariate normal with mean equal to this, and variance will be the square of this quantity in the denominator, right? So variance is equal to that, sigma square y, 1 minus rho square. So for two jointly normal random variables, the conditional mean is a linear function of x, right? Because the expression that we had over there, right? You can see that the conditional mean, see the conditional mean of y given x, right, is basically a linear function of x. X appears linear in here, okay? So in this case, the best predictor, right, or the optimal predictor is actually a linear predictor. So if you look within the class of linear predictors, you are not giving up anything, linear predictors or linear estimators. And we can actually calculate the COD. So for two jointly normal random variables, the conditional mean is a linear function of x. All right, that is the optimal mean square estimator is linear. And furthermore, if you look at the error of that optimal mean square estimator, that is given by this variance that you have here, sigma square y 1 minus rho square. And therefore, the epsilon opt, in the COD definition, you had epsilon dot minus epsilon opt over something, all right? So epsilon opt is given by this, sigma square y 1 minus rho square, right? So since in the absence of any data, in the absence of any information on x, all right, the best estimate is the mean of y, all right? And the error of the mean of y is basically the variance, all right? So you can plug that into the COD definition and you can calculate that the COD, right, for the optimal predictor, which is also the COD of the best linear predictor, is going to be given by epsilon dot, that's sigma square y, minus epsilon op that you calculated, divided by sigma square y, and that's equal to rho square, okay, which is basically the square of the correlation, right? So in this case, we are able to get a closed form expression, right, and we actually have the best predictor also, well within our reach, because the conditional density in this case is Gaussian, right, and we can derive it quite easily. Okay, so this is also going to be used in the paper that I'm going to discuss today, right? So that's why we discussed all these extra things like asides, okay, so that we can, when we are going through the paper, we are not going to have to stop and explain all this stuff. So are there any questions on this material? Okay, if there are no questions, right, then we are now ready to actually go ahead and discuss the COD paper, right? So this is, and I believe you already have a PDF file of this paper, right? So this paper is basically concerned with the general nonlinear framework for the analysis of gene interaction via multivariate expression arrays. Okay, so here you have looked at gene expressions across different conditions, and you're trying to find out relationships between genes. Okay, which gene is related to another gene, to a particular gene. So if you have a target, which are the best predictors for that target? Okay, and then you have a choice here because you might have 10,000 genes on the microarray. All right, so if you pick one target, you have those other 9,999 genes. Okay, that are potential predictors. Okay, so you can get all kinds of combinations, right? I mean, you have 9,999. You could say that, okay, any two genes will predict that gene. Okay, three genes. Okay, so there are lots of different combinations that you can try out. And if you want to exhaustively evaluate all these different combinations, it's going to be a lot of computational effort, right? But typically they do it with two or three of them, right? So the idea here is, how are you going to pick up the best predictor? You're going to say that, the set which gives you the highest COD, right, the COD close to 1, that will be the good predictor for that gene. Okay, so you're trying to find out, by looking at gene expression data, you're trying to figure out relationships between genes. Okay, that's the main idea here. Okay, so this is prediction, right? So you observe the expression of some random variables, right? Based on that, you want to make a guess about the expression of some other random variables. And usually the quantization will be binary, like 0, 1. So this is very much like a classification problem, right? Except that the feature vector is what you observe, right? Feature vector is what you observe, and then based on that, you're going to spit out a class label, right? Either 0 or 1 or 1, 0, minus 1. Okay, that's what this particular paper talks about. Okay, it tries to develop the machinery for that. Okay, and I will go through it slowly, and I'm pretty sure that you'll be following most of it, right? So for the CDNA microarray, I don't need to explain anything because we have already covered that in detail, right? So all this stuff is basically about the biology, about transcripts, how the microarrays are done and all that stuff. But now at the end of the day, you basically have a microarray slides with a bunch of ones and zeros, 1, 0 and minus 1, okay, if it is ternary quantization. And you want to use that information, right, to come up with the predictors for a particular gene, right? If you want to be able to predict the expression at spot number 10, based on expressions at spot number 7 and spot number 9. Okay, and you do not know a priori which genes to use as your predictors. Right, so that's the problem that they're trying to address here. Okay, so here is this diagram, right? So based on your measurements of X, all right, so these could be some of the genes on the microarray. You're trying to make a prediction for this variable Y. Okay, Y is some function of all these variables that are going in, and some others. Okay, there are latent variables, but I want to use the data that I have, right, like expression of X versus Y, the data that's given to me, to come up with a predictor, right? Now, what is the form of this predictor? It could be a very, very complicated function that you come up with. Then you're going to need tons of data to infer that particular predictor, right? On the other hand, you might make simplifying assumptions, like you might say it'll be a linear predictor, something maybe with a linear predictor and some slight nonlinearity, right? The choice is yours, right? So this paper basically deals with nonlinear multivariate prediction, and it is in a setting where you have like ternary data, okay, because in the microarray we have already seen you have the red channel, green channel, right? Red over green is almost 1, right, the ratio. It's significantly higher than 1, significantly less than 1, okay? So there are 3 possibilities, and we will denote those by 1, 0, minus 1, right? So you want to come up with that kind of function, right? So that kind of function, right, can be represented, so you can either represent it using an expression, right? Or you can represent it by just some measurements that you have taken, right? So, I mean, like, if you're trying to represent a function, you can either provide a closed form expression, right? Or you can provide values, right? The values of x and f of x, that will also define the function. So here, if you're looking, for example, here you're looking, let's say, for the most general nonlinear, and if there is a question anywhere, just stop me, okay? I'm going to try to help you to read the paper on your own, right? Hopefully you'll do that, right? But again, I mean, if you have any questions, just stop me, right? And we'll explain. But I think I have covered a lot of the preliminary material in the last lecture and what I covered using that PDF file just leading up to this paper. So the most general nonlinear predictor or filter for discrete data can be represented by a logic table, all right? Because here everything is discretized. So for ternary data, you have three possible levels for each variable, -1, 0, +1. The table is going to have a row for each input variable, like x1, x2 here, right? All the different possibilities, right? -1, 0, and 1, right? And then, and 1 for the output variable, right? So if there are m variables, right, because here it is ternary, right? If there are m variables, then you are going to have 3 to the power of m columns, because there will be 3 to the power of m possible combinations that you will get using these variables, right? And there will be m plus 1 rows, because one row corresponding to each variable, and then the final row for the output, okay, that you are predicting, all right? Now there are many ways to represent, mathematically represent nonlinear predictors, including via logic circuitry. So the basic task here is to design nonlinear predictors from the data, right? Quantitatively, the problem is straightforward. The theoretically optimal predictor of the target y based on the predictor variables x1 to xm is unknown and must be statistically estimated, right? And the theoretically optimal predictor has minimum error across the population and must be designed, estimated from a sample by some training or estimation method. Now the degree to which a design predictor approximates the optimal predictor depends on the training procedure and the sample size. Okay, we know that if you have small sample size, you're not going to be able to get good estimates, all right? So even for a relatively small number of predictor genes, precise design of the optimal predictor requires a large number of experimental applications. We have talked about this. Even in classification, you had the same problem, okay? And prediction is no different than classification, right? So we will go back to that picture that we had before, right? I think that's the picture that is coming up, all right? So it's not something new, right? See here, just like we had in classification, we had the Bayes error here, right? The error of the optimal predictor without imposing any structural constraints, right? The best predictor over all classes, is this one. Let's say that's the error. Now the problem is you are going to have to design the predictor from the data, okay? Nobody is going to give you the probability distributions and all that. So if you design from the data, then it's basically a random variable, okay, because it depends on the sample. So you have to look at the expectation. Well, the expected value of the error is going to approach the error of the optimal predictor, right? Optimal nonlinear predictor as the sample size goes to infinity. But for small sample sizes, you have a problem, okay? There is a big mismatch here. So what do? You put some constraints on the predictor. You might say, I'm going to use only a linear predictor, right? Okay. In the process, you have up the error for the optimal design, because the optimal linear predictor obviously will have a higher error than the optimal predictor without any constraints, okay, on the class, all right? You have up that, but the linear predictor is much easier to estimate, okay? So especially with smaller samples, the difference between the error that you make in trying to estimate this constrained predictor, right, and the error of the optimal predictor, that'll be a lot smaller. Okay, so if you're operating in this region, which is going to be typically the case when you're working with microarrays, you will work with constraint predictors. Okay, it might be linear or maybe linear with some nonlinearity put on it. You're not going to just look over a general class of nonlinear predictors. You're not going to work with that table for ternary data that I showed you, because that has got too many possibilities and you don't have enough data to infer all the entries in that table. So here, all this stuff, all right? All this stuff here is exactly the same kind of discussion that we had for classification, right? If you remember why we put constraints and then you looked at that curve and all that stuff, exactly the same kind of discussion, right? And then, So having gone through that discussion, we decide that, okay, we are going to put some structure on the predictor. We're not going to say it's a structureless predictor because we don't have enough data to infer it. Okay. So what is the structure that you're going to choose, right? So figure 2, which we just already skipped. I think figure 2 is the next one. Okay. I think that's the design, the problem that we discussed, the design problem. Okay. And so the class of predictors that we are going to pick, right, they are made up of what are called perceptrons, okay, which is basically you take a linear combination of the data, right, like you have these variables you're observing. These could be genes on the microarray, A1 x1 plus A2 x2 up to AM xm plus B, right, and then you put it through some thresholding function, okay, because you have three classes here, 1, 0, minus 1, okay. If this thing is great, if this argument is greater than 0, it'll split out 1. If it is less than 0, it'll split out 0, right? Alternatively, you could have ternary perceptron where you'll say that this is going to split out 1 if this quantity is, I think, greater than 0.5. It'll spit out minus 1 if this quantity, this argument is less than minus 0.5, right? And in between, it'll spit out 0, okay? Now, in the process, you have really decreased the number of variables because in order to specify this predictor, this function, you know, this is a thresholding function. All you need are the coefficients A1, A2 up to AM, right, and B, okay? Whereas in the other table that I gave you earlier, you have many more variables to fill up, okay? Lot more stuff to learn from the data. Okay. So here he does some calculations. There are 3 to the power of 9 possible two-variable ternary nonlinear predictors from that table, right? But here the number is only 417, right? So I haven't gone through the calculation leading to that 417, but it's obviously a lot smaller than 3 to the power of 9. Okay, you can check that. And the design of the perceptron will require estimating these coefficients A1 through AM and then B, right? And in the appendix, he provides an algorithm for a training algorithm, an update algorithm for estimating these parameters. Now, one way of constraining predictors which are less constrained than perceptrons is to use neural networks, right? So here it's just one linear function and then one nonlinearity. Okay, in a neural network you'll have multiple layers, multiple linear combinations going in through one nonlinearity, then again another set of linear combinations going in through another nonlinearity, and so on. Okay, so you can use that, but again, I mean, you'll have more flexibility, but you're going to need more data. Okay, because if you make your predictor function more complicated, you're going to need more data to learn it. And data, at least in cancer genomics, is very, very scarce, right? So this is the discussion about the two-layer neural network. You have a linear combination of the weights going through one nonlinearity, then again a linear combination of this thing going through another nonlinearity, and you can have many layers, okay? Now, do you know why neural networks are so popular, or anybody?
They're good classifiers.
What?
They're good classifiers. They
Are they good classifiers? Not necessarily. Like if you don't have enough data, you won't get a good classifier, right? No.
easy to use.
Well, I mean, one of the reasons I think they're so popular is that there's not really very good theory for them, okay? So anybody can use them, okay? I run my neural net, okay? But what the neural net is in reality is it is basically a function approximator, right? Some guy has shown, okay, guy or gal, okay, whoever it is, many years ago that, you know, any function, right, can be approximated. I think a continuous function on a compact set, it can be approximated to any degree of accuracy, right, by using a neural network with sufficient number of neurons, okay, right? So, but you have to, so if you're trying to approximate some function that you don't know, right, you can probably use a neural network, you know, it'll have enough flexibility that if you choose the weights right, it will approximate that function, okay? So that's where the interest is, but the thing is you have to know those weights, okay? If you use a very complicated function, right, then, and you don't have enough data, right, you use too complicated a function, then it will be an overfitting problem, right?
There's many heuristics to train the neural network as in determinate weights.
No, there are heuristics, okay, but again, I mean, you know, it'll go to local minima, okay, you don't have global minima, right, you have local minima. Now, if you want to look at the basis for that stuff, one of the things that is used in neural network training is called the backpropagation algorithm. That is basically the gradient descent, okay, and if you want to really learn about that area, you have to look at the area of adaptive control, adaptive systems, adaptive identification and control, because in that area, it's not for a nonlinear system, okay, but all these techniques are developed with provable guarantees of convergence, stability, robustness, and so on, okay. Here, nothing can be, because the cost function is not convex, okay. So there is a problem. So you don't have a global minimum. You have local minima, right, and you really cannot, you can get only local type results, okay. But again, it's fertile ground because in adaptive control, all those problems are solved, okay. So people are out of business, okay. There's no work. Here, there's nothing is done, so you can, tweak things around, run more simulations, and do it. So that's the advantage, okay. And anybody can do that, And if you tell somebody that you're going to do something using, let's say, linear systems, you're not going to get any money, right? But if you do with neural networks or intelligent stuff, really you're doing nothing. You're just tinkering around, but you would get money over there, okay? So simply because it's not a and there are people who have even done with fuzzy systems, all right? Those are also universal approximators, all right? So there are people that have done that, And why would I use a neural network or a fuzzy system? I could use a polynomial, But the problem is if I use polynomial or cubic spline, nobody's going to give me money because that's already there worked out in the math literature, right? So, but anyway, that was just an aside discussion. I'm not trying to downgrade anybody or insult anybody. But that's the state of the art. But anyway, this is a neural network, and here there is a diagram that is showing you how you could use a neural network to approximate a function, right? See here he says that a key problem with using neural networks for microarray prediction is that multi-layer stochastic training can be very imprecise when data sets are limited. And in this paper we restrict ourselves to unconstrained perceptron predictors. See, because here if you're doing linear system identification, you need sufficient frequencies in the input signal, right, in order to be able to identify your parameters, right? Like if you're doing, for example, if your system, if you're doing like frequency response, right, you have magnitude and phase. From 2 bits of information, you can identify 2 parameters. So for every frequency, you'll get a magnitude phase. So you will need really, for a linear system, it has been shown in the adaptive literature that if you have n parameters, you need n over 2 distinct frequencies so that you have n spectral, what I call n spectral lines, okay. And there is, I'm not advertising for my course, but there is a course in adaptive control that I do teach, once in a while, and we cover some of those things, okay. But in this, because it's nonlinear, right? See, if it's a linear system is not going to produce any new frequencies. You excite a linear system with a sine wave, it is going to produce a sine wave with an amplitude change, all right, and a phase shift, right? In a nonlinear system, you do the Fourier analysis, it's going to produce a whole bunch of different frequencies, okay? So nailing things down, like what is it going to take, okay, how many frequencies are you going to need to get the parameters to converge is a different story, right? But it's a fertile area because if nothing can be proven theoretically means people are not going to be out of work, okay? You can just get a new application and run this and you have a research problem, right? Okay, so now to get back to our stuff. So this is a question of how you're going to, what kind of structure you're going to use for the predictor. In this paper, they're using a perceptron. If somebody wants to, they can use neural network. They can use whatever else they like, right? But at the end of the day, you want to find out the coefficient of determination, all right, which will help you to, figure out association between genes, okay? So let's take a look at this. So if y is a real valued random variable and let's say the error that you're using is the mean square error, all right, then the expected value of y predicted minus y absolute value square, right? So the mean square error is the criterion that you're using. Then the best predictor of y in the absence of any observations is its mean. Okay, we know that. I already proved that in the last lecture, right? And the error of that best predictor in the absence of any observations is basically the variance, right? I showed that to you. Now the best unconstrained predictor of y based on the observed real valued variables is the conditional expectation of y. I showed that to you too, right? Given these observed variables, right? So there is no general moment expression for the conditional expectation, right? In general, you don't have that, okay? You need to know the conditional density and then you have to calculate from there. However, there is one for the best linear predictor, right? And this is something that I derived last time. That's why I did all those derivations, okay? So its form is that of equation 2 absent the threshold, right? Where equation 2 was basically that linear combination, I think, without the... Yeah, go ahead. Yeah, it's basically this, If it's linear, then you won't have the thresholding function. The thresholding is going to make it nonlinear. Okay, so the optimal coefficients are determined by the vector equation A equals R pseudo inverse C, all right? where R is the autocorrelation matrix for the random vector V, and C is the cross correlation vector for Y and V, and R plus is the pseudo inverse. Okay, I derived this, all right, last time. If you look back in your notes, all right, all that is derived when I talked about the orthogonality principle and all that. So for digital processing, all predictors, including the conditional expectation and the optimal linear predictor, must be quantized if you're going to do digital, all right, not analog. Now the coefficient of determination of the optimal predictor is the relative decrease in error due to the presence of the observed variables, right? So you want to see, okay, what is the error of the best predictor without any observations, right? Then you make the observations, right? Am I doing any better, right? In the presence of the observations of, excuse me, I designed the best predictor, right? Is that any better than what I was doing before, right? If not, then I might as well not make any observations, okay? Not talk about any relationships between what is observed and what you're trying to estimate, right? So this is the basis of the formula for the COD that I already talked about, right, when we went through the PowerPoint slides. So theta opt is epsilon dot minus epsilon opt over epsilon dot, where epsilon dot is the error for the best predictor in the absence of observations, okay? That would be the error associated with the mean, which would be the variance, all right? And in general, this will be a number between 0 and 1, because hopefully when you made observations, you're not doing any worse, all right? You're doing a little bit better. So, if with observations your error goes to 0, then you'll have a COD of 1. If with observations your error doesn't reduce, it's still epsilon dot, you'll get a COD of 0, right? So that's the idea. So in statistics, and many of you here have very strong background in statistics, the coefficient of determination has been used to evaluate the significance of multiple linear regression, right? So you must be familiar with that, okay? And it has been recently used in nonlinear digital signal processing. Now for linear predictors, you can get a closed form expression, which is what I showed you at the beginning of this class. So, right, for linear prediction using the mean square error, the coefficient of determination can be analytically expressed in terms of second order moments of the observation and the target, right? And I derived this expression, right? It's there in the note, additional notes that I gave you, where rho is the correlation coefficient. And if we employ only the correlation coefficient between two variables, all right, then we can see that the COD actually works out to being the square of the correlation coefficient, right? That's what I did at the beginning of this class, right? Now for most nonlinear predictors, right, you're not going to be able to do that, okay? You cannot get closed form expressions. So including perceptrons, which is what we are going to use, there is no moment expression such as equation 5 for the coefficient of determination. And for the unconstrained ternary predictor, theta opt will be given by this expression, right? Where, this is the error when you're predicting y using its mean, right? Okay. So y, actually it's y using the thresholding function applied to the mean. Okay. Because here you have a perceptron, so you have this linear thing, and then that is passing through a thresholding function, right? So that is epsilon mu, and then this is the error that you get from the predictor that you come up with, right, using all the data, right? Now if you're going to get this the COD in the case of constrained prediction, right, then this will be replaced by epsilon opt constraint. Okay, that's what is being done here, right? All right, any questions? Now the problem is that I don't know these guys, okay, because this business of predicting y by the threshold applied to the mean of y, okay, I don't have the mean of y, right? So I have to find the mean of y, okay? So I have to learn everything from the data, right? So now this becomes basically a design problem, right? Because if it's a textbook problem, you'll give me the probabilities, I can go and do the calculation, like some of the ones that you have done on homework number 2, where you did Bayesian classification and all that. But in the real world, you're not going to have that information, right? So you have to learn from the data, right? And then, obviously the expectation of this one is going to be larger than or the error is going to be larger than what you would get, right? Than the performance of the best possible predictor, okay? And so in that case, that for small sample sizes, all right, you're going to be way off, all right? So you have to put constraints, right? You have to do some kind of constraint prediction, right? Maybe using a perceptron or something like that, okay? And this is again that same discussion, right? The same discussion about, what the effect of the constraint would be on the coefficient of determination. And the idea here is, given a particular target gene, right, I can come up and let's say I decide that I'm going to use only 2 genes to predict it. Okay, I will look over all these expressions on the microarray and figure out. Okay, for each of them, I will try to figure out which set of 2 genes is going to give me the smallest error, or which set of 2 genes is going to allow me to reduce the error the most, right? And based on that, I will calculate the COD. So the ones which have high CODs, those are the good ones. Okay, so you want to, this method is basically a statistical method. There's no cause and effect here. You just look at the numbers, and based on that you make predictions about which genes are likely to be related to which ones. Okay, and this was done there was data, experimental data that went into this paper. I'll talk about this in a few minutes. And for that in that data, the biologists actually threw in a couple of fictitious genes also. Like, some fictitious gene is, let's say, some function of the other predictors. Okay, and they wanted to see whether this method could pick it up. Okay, and it did. Okay, it did pick up those associations, as I'm going to point out in a few minutes. Right. So, all right. Any questions? Now here, see, the problem is you want to design the predictor, okay? The best predictor. You also, in order to calculate the COD, you need an estimate of the error of the best predictor, because it's the error, okay? The error of the best predictor minus the error of the best predictor when you have observations divided. So you need to be able to calculate those errors, okay? How are you going to do that? Well, you need to do error estimation, okay? Same kind of methods that you use in classification, like resubstitution, right? Cross-validation, bootstrap, whatever, Same thing, then nobody is telling you which one to use, because there are no theoretical guarantees anywhere. Okay, so you're going to use one of those methods and get your error estimates, and then you will calculate the COD from that. Okay, so there is quite a lot of theory that goes into this stuff, and some of that is in the appendix. But we are going to move on to the actual example. Right? So this talks about cross validation, right? Resubstitution, right? So which one you should use? Then there is the issue of feature selection. Okay, how many predictors are you going to use? Right, if you use too many predictors, again you will have problems. Okay, because you don't have enough data to learn. Right, so the feature selection problem is haunting you again. Right, but let's say those have been figured out. You decided you're going to use 2 or 3 predictors, and you ran your algorithm, your software, right, and you came up with the CODs. Okay, then now based on the CODs, you would be able to, figure out the association between different genes, even use this information to come up with regulatory networks and so on. Okay. Again, cause-effect relationship not captured here, only associations captured. Right. So let's move on to the biological example. Right. So again, if you like this kind of math, or you're really interested in this, read the whole paper in its entirety, because it has the math and all that worked out at the end, right? And it might refer you to some other papers. Right? And another thing I should point out is that, this paper was published in 2000. Okay, let me show you. Okay, look, these guys. Okay, this is Joe Dirishi, all right, and he's out of let's see, Pat Brown's group from Stanford. They were the first ones that did the microarrays, right? Okay, in 1996. See, Joe Dirishi, Pat Brown. So he was, I think this guy has moved to UT Austin. I'm not sure, but he probably did. Okay, but has he? Okay, but I'm saying that he was a postdoc in this lab. And see, these are publications in Nature Genetics and Science. Okay, because they were the first ones that did the microarrays. Now that paper, the one that we discussed, the ratio analysis paper, that is also one of the first papers on microarrays. Okay, and I believe Mike Bittner is probably on one of these. Okay. See, you guys will feel good. You came to the right place. See, Mike Bittner is here, right? So, he's been associated with these things since the early days of the microarrays, right? And that ratio analysis. So these are the 2 of the first papers on microarrays, and the third one is the first paper on image analysis of microarrays. That's the paper that we already discussed. Right? So anyway, going back to our discussion, right? See, this is, they use stress response data, right? So tests of the ability of both the full logic, that is unconstrained predictor, and the perceptron to detect associations based on changes in transcriptional level have been performed in the context of responsiveness to genotoxic stress, right? As a result of a microarray study surveying transcription of 1238 genes during the response of a myeloid line to ionizing radiation, 30 genes not previously known to participate in response to ion were found to be responsive. I think this is the other paper that they are referring to. Let me see. Let me just make sure. Okay, is that right or no? Let's see. 18. Okay, so is that? I'm not sure whether it is that or something else. Okay, let's look at 18. Oh, no, this is something else. This paper, all right, 18. Sally and Munson, yeah. So this is about fluorescent cDNA microarray hybridization reveals complexity and heterogeneity of cellular genotoxic stress response. But anyway, they had done the work on this, okay, where they zapped the cells with ionizing radiation and looked at gene expression, right? And that same data they're going to, I mean, in this paper they figured out that, running this kind of experiments uh, pointed them in the direction of 30 genes that they didn't know earlier were involved in this kind of response, right? So to further characterize the responsiveness of these genes to genotoxic stresses, the responsiveness of a subset of 9 of them was examined by blot assays in 12 cell lines. Okay, and you guys now know what blots are. Okay, the southern blot, western blot, and all that stuff. All right. By blot assays in 12 cell lines stimulated with ionizing radiation. That's one stressor. A chemical mutagen, right, or ultraviolet radiation. The cell lines were chosen so that a sampling of both p53 proficient and p53 deficient cells would be assayed. And as a blind control, expression patterns for, see, I told you about the two fictitious genes that were created, okay? And they call them AHA and OHO or something like that, okay? Now, so you do this kind of analysis, okay? I mean, you have this data, then you have the predictor. It's up to you to choose whether it's a perceptron or whatever, but then based on that, you did the error estimation for that, and you came up with the COD, okay? And then they have the COD diagrams that they have drawn for various genes, right? So you can see. So this is the set of cell lines that was used, okay, see? So these are the cell lines, these are the conditions, ionizing radiation, then that methyl, whatever sulfonate, all right, ionizing radiation and so on, ultraviolet radiation, and again everything has been quantized to zeros and ones, okay? So this is the data that they had, okay? And these are the genes that they're looking at, right? BCL3, then that's probably involved in apoptosis. P53 is there, P21 is there, MDM2 is there, okay? So you've seen some of these genes, at least P21, P53, you wrote about it on the exam, okay? So it's not like something way out there. It's something you have some, and then these two are the fictitious guys that they made up rules for, okay? Now, looking at this data, can you figure out those relationships? That's the question, right? So they were able to figure out many of these relationships, right? And these relationships are represented in these diagrams, right? Like see here, if this is the target, if you predict the target using only predictor 1, the COD is theta 1. If you use both predictor 1, predictor 2, the COD is theta 2. If you use predictor 1, predictor 2, predictor 3, the COD is theta 1. Okay. So you have several of these diagrams. Like this is the one I presented to you earlier, right, with P53 and MDM2, right? So you can see if you just use P53 to predict MDM2, it's 0.473. Then if you use if you use take P53 as the target, oh, this is the one I discussed earlier. This is the one that was there in my PowerPoint notes. If you just use P21, it's 0.227. Okay, if it's just M2, it's 0.259. Use them together, the COD jumps up to 0.452, right? And this paper has a listing of many of these other CODs. So some of them were known from before, some of the other ones were discovered, okay, in the course of this work. So, in fact, I think it has an entire table, see? Like it has all these different COD diagrams, okay? So, and you're trying to see what the difference is between the perceptron, okay? If you're using perceptron and the full logic, that means using that table, that ternary table, right? So you can see what the CODs look like, okay? This, and so on, okay? So many cases are covered here, right? And here, of course, there is some discussion about, which error estimation you should use, okay? Whether you should use resubstitution or cross-validation and so on, okay? And if you're interested, if you're statistically inclined, I encourage you to go and read that stuff, okay? But from an engineering point of view, it's basically about figuring out relationships between genes, okay? which are the best predictors for a particular gene. Okay, if I want to improve my knowledge about the expression status of a particular gene, looking at some other genes, okay, which are the predictors that I should use, right? That's the kind of problem that is being answered here, okay, and it is being formulated in the context of non-linear prediction, okay, using a non-linear predictor, observing something, and then based on those observations, making using a non-linear mapping to basically predict a target that you are interested in. And there was some software also developed, and that will, you know, basically go ahead and provide some, visual display of which are the highest ranked predictors and predictor sets and so on. Okay, but this paper is quite old. It's a 2000 paper, and I think they have, uh, and these are all the different screens. Like yesterday, Nushin Ghaffari was doing that next gen seek. Okay, like all kinds of screens. So here also you have that kind of stuff. You can do it. And you can see that it'll become very computationally intensive if you have like thousands of genes, if you have no prior knowledge, okay, and you have to look for predictors from scratch, okay. It's a big computational problem, right? I mean, because if it's like 10,000 genes and you're going to choose them two at a time, you have to look at 10,000 choose two combinations, look at all those errors, all right, calculate the CODs and then figure out which ones you're going to use. Okay, so it's very computationally intensive. On the other hand, if you use prior information, you know which one affects which one, you might be able to stick that in and cut down on your work, right? And section 6 of this paper discusses the statistical considerations, and I guess this is the kind of stuff that Dr. Doherty really likes, right? All those bounds and all that are available in the literature. So again, I mean, if you're taking courses in that, you're going to work on the theoretical aspect, then you might want to take a look and read that stuff over there. And this last, so this is the logic circuitry for the perceptron, right? For the predictor, in one of the cases, they've given the logic circuitry. And then the last one is about perceptron training, maybe like backpropagation algorithm, right? Something similar to that, right? And you update it, and if the error falls below a certain value, then you say you have converged. Right? So that's the discussion of this paper, right? So are there any questions? So I think I have covered enough material, okay, in that explanatory material that I gave you, so that if somebody is interested, they can go and read the whole paper, right? Because all the difficult steps, I have put those in. In fact, I had to work those out myself because my background is not in this area, okay? So trying to read that paper, and I'm not a stochastic person, okay? So all those, minimum mean square error estimate and all that, that's not like stuff that I dream about. No, there are equations I can do, like when I teach the adaptive control class, I tell them, that don't worry about this, after some time you'll be able to derive it in your sleep, okay? But not these, okay? So I had to spend some time learning this, but you can do that, and especially most of you have pretty strong background in statistics, stochastic processes, and the like, correct? Now, so that finishes our discussion of this paper, right? So next time I'm going to get started with intervention, because based on this, okay, based on this kind of data, I have already shown you how you can come up with regulatory network. Not necessarily the true network, okay, but you can definitely take this information, construct a probabilistic Boolean network, right, and then look at the dynamics of the network, right. So the next topic that we want to look at is, if you don't like the dynamics that you see, okay, the network has been altered, okay, how do you intervene in the network, okay, what would be a judicious way to try to, intervene in the network to move its state from a bad situation like that's causing cancer and metastases to something that is like more normal, okay, or induce the cancer cell to go and kill itself by committing suicide, that is apoptosis, right? So things like that I will talk about, okay. Those are the only things that are remaining, right? Intervention and control and so on. I will get done. I'm reasonably confident that by the end of next week, I will getting done with all the material that I have to lecture on, okay. So the presentations could start even as early as maybe even next Friday, okay. So I mean, some of you have asked me, so I think it's time for you to start preparing. And I will hand out 3 more homeworks, okay. One, yeah. Yeah.
So many
Oh, you don't want those? Or?
we have presentation to do and so many
Okay,
homework.
no. See, it's not to force you. It's not to force you, but I don't want you to leave the class thinking that you didn't have to do enough work. So right. I mean, say, oh, I learned some biology. Again, I mean, we could even make those optional or something like that. That's fine too, right? But for people who really want to learn the material, or maybe do you already know the material or you don't? Did you learn anything doing the homework, so it was just a waste of time, or it took up too much of your time? No, I'm just asking.
To
Okay.
You get the idea, understand it. And first, maybe one question or one example, but the
Yeah.
No,
Yeah,
several
always
ones
doing
is
the
labor
same.
intensive.
yeah, yeah. So, uh,
Like,
okay, maybe then what I'll do is, I will give out the homeworks, all right? You decide, okay, how much you want to do, all right, and turn it in, all right? Well, I mean, I don't know how you, huh?
what?
Or you won't turn in anything, huh?
No, no, no.
No, because this is
If
grad
someone
students.
goes and does everything, then if the rest of people, then the
Yeah, but this is a grad class, okay? People will get only A's and B's, okay? You're not going to get D's and F's, right? So, so, I mean, like,
Like,
no,
what are
no,
you
no. What we could do is I will hand out like three more homework. So all of them are not that long. Okay, the second one is probably the longest, the one you did just now. Okay, so it's not. What you might want to do is maybe we take the best four or something like that. Among the homeworks. All right. We could do something. We'll see. Okay, don't worry. Okay, this is a new experiment that I'm trying this time. Okay, because then people will think they got more out of the course. All right. So, or you don't agree, or I don't know. I thought so because this was an exercise for undergrads. Okay, so I mean,
we are not
huh? You're not undergrads. No, I mean like,
but last semester they just got two midterms and
they don't
the
have
presentation, and
presentation,
that's
right?
it. No.
For undergrad, they don't have
why did
presentation.
you find out from those people or what?
Yeah.
No, no, but see the problem with that is that the presentation is very heavily weighted. Okay, so if you don't do a good presentation, right, and then you get a B, right, which has happened in one or two cases, then people are not happy,
Yeah,
right?
we will have spent more time on presentation. So for the homework, like there are so many similar questions on the homework. It's
Yeah,
really
yeah, yeah, yeah.
takes more time, sometimes on.
Okay. Okay, yeah, let me see what we can do. But again, I mean, get ready for the presentations, all right? Because they could start as early as I said.
So will the presentation before Thanksgiving or after Thanksgiving?
All the presentations.
Yeah,
I don't know whether will all of them will get done or not because there are 17 people in the class, so you need 6 lectures. Okay, even if 3 people present every day, right? You need 6 lectures, all right?
can we like choose the dates by ourselves, or you are going to assign the date?
No, I will look at the roster, right,
Okay.
and just go in the alphabetical order. Okay, so whoever that is, so who
Alphabetically.
yeah, yeah, alphabetic by last name. That's what the roster does, right?
I'm the first one. Yeah, first
Yeah,
person.
so you better get your presentation ready. It may not happen until the Monday after next week, but I'm just saying that. Have you chosen a paper?
No.
So then you can talk. I know there are 2 or 3 other people that have asked me. Okay, you can probably talk to them and see if they'll do it. Okay,
No,
because
no. I sent an email today to you with
oh,
the
you did.
paper, and
You sent an email, or
no,
you?
I'll send. I
Oh,
will
okay,
send you an
okay,
email
okay,
with the
okay.
paper.
Yeah, yeah,
Can
yeah.
we like do some like joint presentation, like two people do the same?
Then I give you half the points. How about that? By the way, this is something from my undergrad days. I think somebody went and asked, because it's like 4 people doing the lab, so they wanted to submit a joint report. The professor said, okay, I'll just split the points into four and give. So
But
no, well, I mean, if it's joint, then it'll have to be like
like two
two
multiple
presentations. Yeah,
times,
yeah,
right? Oh,
and you have to make sure that it's clear that both people are doing the
no,
work.
I was just wondering.
No, no, it's possible. Okay, I mean, like if it's some real important paper. Now, the question that I have for you is like on the Wednesday before Thanksgiving. Okay, do you guys want to take that off, or you guys really don't care?
Actually, I know that we have a time slot for the final. So how about using this one? Is the final
No, no,
equally
no.
important?
No, no, no.
No,
We'll get done long before then.
Okay.
Yeah, yeah. What is the time slot for the final? Do you know what it
it
is?
should be Monday or Tuesday.
Yeah, that's time for you to get extra sleep. So after you work really hard or something. So,
Just to be
yeah.
sure.
I'm
No, no, no.
confused.
No. See, the time slot for the final is very tricky because, you know,
It's a
i-
Friday.
yeah, and it might be like the day before the grades are due. Okay, I mean, like,
Okay.
yeah, it can be because these are graduating people. It's like they have a final on Wednesday, and then Thursday by 6 p.m. they want all the grades. Okay, in this class it's not difficult because it's like 17 people, but let's not push things off that far. So. But I think we can get started because already 3 people have mailed me. So at least one lecture is covered. Okay. I mean, like, I'm assuming that, and everybody is here, so they are probably preparing for the presentation, all right? And again, I mean, if you think that the homework is too much of a burden, we at least had 2 homeworks that you guys turned in. So I can, get the grader to grade that and use that for the points. My main intention was I didn't want to have so many points concentrated just on the presentation, because there are people, no matter how hard they try, they may not do a good presentation. Okay, simply they're not. I mean, they haven't mastered the art of presenting. All right, so then it becomes a little bit difficult for me. Okay, I mean, like so, all right, to assign the grade.
If any just related to the biology,
And then
Just related to the biology. No?
like yeah, like more maybe not related to this kind of stuff.
No, it can be related to the biology, but it should have some quantitative stuff in it too.
Okay, yeah.
Yeah, it doesn't have to be our brand of.
Okay, okay.
Yeah, it doesn't have to be our brand of quantitative stuff. Okay, it can be somebody else's brand, but it cannot be like a biology paper. Okay, on something. Yeah.
Right.
I mean, it could be, but that wouldn't satisfy the requirement for a double E course. So.
Well, we could send you a paper and you can
yeah, and
like
you
tell
can
us
like
if
give us the feedback whether we can choose that paper.
Sure, that's fine. That's fair enough. But I think now it is time to start choosing the papers. Yeah.
Yeah.
No, I don't want you to do homework at the expense of this thing, okay? I will send it out, then we'll see what to do, okay? I mean,
Okay.
because I'm telling you, like you did the homework on, what was the first homework on? It was on microarray image analysis, all right? The second homework is on
Classify.
classifier. I think the third one might be on clustering, all right? The fourth one is on this expression prediction, COD. Very simple examples, okay? Like you observe 1, 0, -1. Remember, undergrads have done that before you, okay? And you don't, it might be like 3 problems in each, huh?
I mean, they were complaining, right?
No. They did not complain because of that. Remember, they had no presentation. They did not complain because of that. But the problem is, some of them didn't know 303 knowledge. Okay, all this conditional expectation and all this stuff, that threw them off. Okay, so and in some of the problems, like when you're doing Bayes classification and all that stuff, you have to know some basic probability stuff, right? They were having trouble over there. Okay, that's where the complaint came from. Not from this. I mean, if there's no, they're done with 2 exams and only homeworks are being turned in, it's not something to complain about. Yeah, and they don't have to do a presentation. They're okay.
but we need to do everything.
Yeah, we can do everything.
That's because you're PhD students, right? I mean, you're expected to walk on water, okay? Because you're supposed to come up with stuff that nobody else can see, all right? Whereas for them, they are just doing routine stuff. That's okay. You don't have to do it in this course, but that's the reason why, you know. Any other questions? All right. So please turn in the homework number 2. All right.